Students, this is NCERT exercise problem 2.50 from page number 72 of structure of atom, right? So let's read this statement. The longest wavelength doublet absorption transition is observed at 589 and 589.6 nanometer. Calculate the frequency of each transition and energy difference between two excited states. In this question, doublet absorption transition means if I am considering an electron in the ground state, so this is ground state, right? And we are having electron over here, right? So this electron excites and goes to the first excited state, right? And from this first excited state, again this electron gains energy and goes to the second excited state. Now these two excitations of this electron is known as doublet. That means double absorption means this electron absorb energy two times, and transition means this electron first goes to the excited state 1 and then afterwards goes to the excited state 2, right? Now from this we have to find the frequency of each transition. That means first of all I have to find the frequency of excited state 1 and then frequency of excited state 2, right? In first state, I am having lambda equal to 589 nanometer. In first excited state, the wavelength of electron is 589 nanometer, and in second excited state, the wavelength of electron is 589.6 nanometer, right? So for this, first of all, we'll write the given values. So I am having lambda 1 equal to 589 nanometer and lambda 2 equal to 589.6 nanometer. In this problem, we have to find the frequency of each transition. That means nu 1 and nu 2 and energy difference between two excited states. Now I know that these are two excited states and we have to find the energy difference between these two excited states, right? For this, first of all, we'll find the frequency of excited state 1 and frequency of excited state 2, right? For this, we'll see the formula. So to find the frequency, we'll use the formula nu equal to c by lambda. Now c is velocity of light. So you can write it is velocity of light, and you have to remember the value, that is 3 into 10 raised to power 8 meter per second. Lambda I am having surely 589 nanometer. If you see, this velocity of light is in meter but wavelength is in nanometer. So what I'll do, I'll simply convert this wavelength in meter. So it will be 589 into 10 raised to power minus 9 meter. In bracket you can write 1 nanometer equal to 10 raised to power minus 9 meter. In first case, I have to find the frequency of excited state 1, right? So for this, I'll assume it as nu 1 equal to c by lambda 1, right? So nu 1 equal to c 3 into 10 raised to power 8 meter per second divided by lambda 589 into 10 raised to power minus 9 meter. I'll cancel this meter with this. Now if you see, this 3 is smaller than 589, right? So to make the calculations easy, I'll make this 3 bigger than 589. For this, I'll consider this 10 raised to power 8. So this 10 raised to power 8 can be written as 10 raised to power 5 plus 3. If I am writing powers in addition form, that means these powers are in multiplication. So I can write these powers as 10 raised to power 5 into 10 raised to power 3, right? Now this 10 raised to power 3 means I am having 3 zeros with 1, right? So 10 raised to power 8 can be written as 1000 into 10 raised to power 5, right? So simply replace this 10 raised to power 8 with 1000 into 10 raised to power 5. So nu 1 equal to 3 into 1000 into 10 raised to power 5. Now this 10 raised to power 9 is negative in denominator. When I'll take this value in numerator, it will change its sign, right? Divided by 589, right? Unit I am having second inverse only. Now 3 into 1000, it will be 3000 into, these two powers are in multiplication, so you can simply add them. 10 raised to power 5 plus 9 divided by 589 and units second inverse, right? Now when you will divide 3000 with 589, your answer will be 5.093 into 10 raised to power 14 second inverse. This is the frequency of excited state 1. Now we will find the frequency of excited state 2. For this we'll use the formula nu2 equal to c by lambda 2. Now c is definitely velocity of light and its value is 3 into 10 raised to power 8 meter per second. Lambda 2 is definitely wavelength of second excited state. So that is 589.6 nanometer. Again, we will convert this nanometer into meter. For this, I'll multiply 589.6 with 10 raised to power minus 9 and this value will be converted in meter, right? In bracket, again, you can write over here 1 nanometer equal to 10 raised to power minus 9 meter. We'll simply put the values. So nu2 equal to 3 into 10 raised to power 8 meter per second divided by, now this lambda 2, it is 589.6 into 10 raised to power minus 9 meter. I'll cancel this meter with this. Again, 3 is smaller than 589.6. So what I'll do, I'll simply convert this 3 higher than 589.6. For this, I'll consider this 10 raised to power 8 as we have done before. 10 raised to power 8 can be written as 1000 into 10 raised to power 5, right? So 3 into 1000 into 10 raised to power 5. This 10 raised to power minus 9 can be written as 10 raised to power 9 when I'll take it in numerator, divided by 589.6 units second inverse, right? So 3 into 1000, it will be 3000. These two powers are in multiplication, so again you can add them. So 10 raised to power 5 plus 9 divided by 589.6 second inverse. Now 3000 divided by 589.6, your answer will be nu2 equal to 5.088. Now 10 raised to power 5 plus 9, it will be 10 raised to power 14 second inverse. I have to find the energy difference between two transition states, right? So for this, I'll use the formula delta E equal to energy of first transition state minus energy of second transition state, right? So delta E equal to, now energy can be find out by E equal to H nu, right? So I'll mention H nu 1 minus H nu 2 over here, right? So you can do it in rough. E1 will be H nu 1 and E2 will be H nu 2. Now I'll take H common, right? So H will be common over here and in bracket I can write nu 1 minus nu 2. Now H is Planck's constant and its value is 6.626 into 10 raised to power minus 34 joule second. Simply put the values. So delta E equal to 6.626 into 10 raised to power minus 34 joule second into nu 1, that is 5.093 into 10 raised to power 14 second inverse minus nu 2, that is 5.088 into 10 raised to power 14 second inverse. If I'm having powers in addition or subtraction, I can take them common, right? So here I am having 10 raised to power 14 with 5.093 as well as 5.088. So what I'll do, I'll simply take 10 raised to power 14 common, right? So I'll mention Planck's constant 6.626 into 10 raised to power minus 34 joules second into Now 5.093 minus 5.088, and I'll take 10 raised to power 14 common with units. So units are second inverse. I'll cancel this second inverse with this second, right? So delta E equal to 6.626 into 10 raised to power minus 34 into, when you will subtract 5.088 from 5.093, your answer will be 0.005 into 10 raised to power 14, and unit is joule only. 6.626 into 0.005, your answer will be 0.03313. These two powers are in multiplication, so you can simply add them. 10 raised to power minus 34 plus 14 joule. Delta E equal to, I just want to convert this 0.03313 according to the scientific notation. So according to the scientific notation, there should be one non-zero digit on the left side of the decimal, right? For this, I'll displace this decimal up to 2 digit, right? So displacement of decimal from left to right leads to the negative power, right? So for this, I can write 3.313 into displacement of decimal is up to 2 digits, so power will be 10 raised to power minus 2 into 10 raised to power minus 34 plus 14, it will be 10 raised to power minus 20 joule, right? Again, these two powers are in multiplication, so you can simply add them. So delta E equal to 3.313 into 10 raised to power minus 2 minus 20 joule. Minus 2 minus 20, it will be minus 22. Delta E equal to 3.313 into 10 raised to power minus 2 minus 20, it will be 10 raised to power minus 22 joule. That means energy difference between two excited states is 3.313 into 10 raised to power minus 22 joule.